Hello children, welcome back to chemistry class. So today class is about amines. In amines, some portion of this we have already studied, and today we will study some portion. What is that? A reaction of amines with benzene sulfonyl chloride. A reaction of amines with benzene sulfonyl chloride. And benzene sulfonyl chloride is a reagent and that is used to distinguish primary, secondary and tertiary amines. So which type of reagent it is? It is a reagent, and this name of this benzene sulfonyl chloride. Here I am writing benzene sulfonyl chloride. Sulfonyl chloride. It is known as Hinsberg reagent. What? Hinsberg reagent. Hinsberg reagent. And this one is used to distinguish primary, secondary and tertiary amines. So let us see how is it useful to distinguish primary, secondary and tertiary amine. So one by one we will discuss. We will take primary, secondary and tertiary, and that basis we will see that how is useful to distinguish primary, secondary and tertiary amines. Okay. So what I wrote here, the formula of benzene sulfonyl chloride C6H5CO2 SO2Cl, and it is known as Hinsberg reaction. What is that? Hinsberg reaction. So it is very important reaction, and this one will be used in lab also to distinguish primary, secondary and tertiary amines. Okay students, let us begin our topic. So when we are taking primary amines, when benzene sulfonyl chloride react with primary amines, it forms alkyl benzene sulfonyl amide. Alkyl benzene sulfonyl amide, which is alkali soluble. Means this one is alkali soluble. We can write alkali soluble. Due to, and what type of group is this? This is electron withdrawing group. This is electron EWC group. So this one is electron withdrawing group. So electron withdrawing group, what happened here? Due to strong electron withdrawing group, hydrogen attached to nitrogen can be easily released. Hydrogen attached to nitrogen can be easily released as a proton. Due to this, it is acidic, and being acidic, it is dissolved in alkalis. So what we have seen here, we seen that when primary amines react with benzene sulfonyl chloride or Hinsberg reaction, it forms the alkyl benzene sulfonyl amide, which is alkali soluble, and due to strong electron withdrawing group. Which one is strong electron withdrawing group? So that one is a strong electron withdrawing group. Due to that, hydrogen atom attached to the nitrogen can be released easily as a photon, and due to this, it is acidic, and being acidic, it is dissolved in alkalis. So this is about primary amines. Okay, let us see secondary amines. So let us see about secondary amines. How does secondary amines react with benzene sulfonyl chloride or Hinsberg reaction? So how does it react? Let us write here. This is secondary amine. Okay, and this is benzene sulfonyl chloride. We get that like this. Okay, so let us see how does it react. Here, this one and this one will react, and they will form HCl. So we can show HCl, and it will form like that: C6H5 SO2 NR. What is this? Alkyl benzene sulfonamide. Alkyl benzene sulfonyl amide, and we can say sulfonamide also. Alkyl benzene sulfonyl amide, or we can say sulfonamide. Okay, so like this compound it forms, students, and this compound is insoluble in alkalis. This compound is insoluble in alkalis because there is no hydrogen atom to the nitrogen that can be released as a proton. So it is not acidic in nature. It is not acidic in nature. So what we can write, secondary amines react with benzene sulfonyl chloride to form alkyl benzene sulfonyl chloride, which is alkali insoluble, due to absence of hydrogen atom to nitrogen. Due to absence of hydrogen atom to nitrogen. So let us write that also. Let us write. So students, what we have seen here, what we wrote here, this reaction can be written like this also. So we can write like this also. Okay, here there I have wrote formula only, and here with symbol I wrote here. Okay, so what happened here, what we discussed, that when secondary amines react with the benzene sulfonyl chloride, it forms the sulfonamide or alkyl benzene sulfonyl chloride, which is insoluble in water because there is no hydrogen atom attached to the nitrogen, so it is insoluble in alkalis also. What we have written here, secondary amines react with Hinsberg reagent to form alkyl benzene sulfonyl chloride. Alkyl benzene, it is alkyl benzene sulfonyl chloride, which is insoluble in alkalis. What is the reason? Why is it insoluble in alkalis? Let us see. There is no hydrogen atom. There is no hydrogen atom here. There is no hydrogen atom attached to the nitrogen atom in sulfonamide. Therefore not acidic and insoluble in alkalis. When it is acidic, then it will be soluble in alkalis. So what we have seen, that secondary amine and primary amine. What is difference between secondary amine and primary amine? We seen that when the secondary amine reacted with the benzene sulfonyl chloride, it also form alkyl benzene sulfonyl amide, and in primary also form alkyl benzene sulfonyl amide. But what is the difference? Primary amine is soluble in alkalis, while secondary amine is insoluble in alkalis. Why it is insoluble? Because there is no hydrogen atom attached to the nitrogen atom. Therefore it is not acidic and not soluble in alkalis. Let us see about tertiary amine. So what we can write? Tertiary amine do not react with Hinsberg reagent. Okay, so what we have seen here, we can distinguish primary, secondary and tertiary amine. Like this I can summarize it. So here we can see that how we can differentiate primary, secondary and tertiary amine by using Hinsberg reagent. Here primary amines react with Hinsberg reagent to form alkyl benzene sulfonyl amide or sulfonamide, which is alkali soluble and acidic in nature. Second, secondary amines react with Hinsberg reagent to form alkyl benzene sulfonyl amide, which is alkali insoluble and not acidic. Third, tertiary amine do not react with Hinsberg reagent and no product is formed. So by using Hinsberg reaction, we can differentiate primary, secondary and tertiary amines. So our next topic is electrophilic substitution reaction. Here we have already seen in the resonance structure of aniline that electron density is higher at the ortho and para position in benzene ring. What? In resonance structure we have already seen that electron density is higher at ortho and para position in benzene ring. Because of that, electrophilic substitution takes place at ortho and para position. If we write the resonance structure of this, we will see electron density is higher at ortho and para position. Okay, and in this, if we see this in this group increases electron density at ortho and para position. So this act as activating group and ortho para directing group. What? This group increases electron density at ortho and para group, so it acts as activating group and it also acts as ortho para directing group. So different type of substitution we will see here. First is bromination. What is that? Electrophilic substitution. That is first is bromination. Bromination. So what we have seen here, that bromination. Aniline react with bromine at room temperature. Aniline react with bromine at room temperature to form white precipitate of tribromoaniline. Aniline react with bromine at room temperature to form white precipitate of tribromoaniline, and what we can write, 2,4,6 tribromoaniline. Okay, but there is complication for the progression of monoproduct. There is complication for the formation of monoproduct. If we want to form only monoproduct, so there is a problem. For that we have to protect this one, this, because it activates much more the benzene ring. To get desired product, we have to protect it by acetic anhydride and followed by hydrolysis, and we get desired monosubstituted product. Let us see. So what they have seen here, if substitution, electrophilic substitution is done by bromine water, it gives us 2,4,6 tribromoaniline. If we want monosubstituted product, so for that we have to protect this group. This group we have to protect because it is more activating group. So instead of monosubstituted product, it forms tri-substituted product. So for this protection, we protect it means this group by acetylation with acetic anhydride, and then substitution is carried out. Followed by hydrolysis to get desired product. Of amines. Okay, let us see what is that here. For preparation of monoproduct, NH2 group is protected by acetylation. What is? By which? Acetylation. By acetylation, it is being protected with acetic anhydride. Then carrying out the desired substitution. When we protect it, then we can carry out desired substitution. Then desired substitution followed by the hydrolysis of substituted amide. substituted amide to substituted amines. So let us see how does it happen. Here aniline is there, it react with this and it form that product amide, and that react with bromine water, and we get this product, and on hydrolysis it give us amines. So to prepare monosubstituted product, what we have to do? We have to protect this group. NH2 group should be protected by the process of acetylation. Then we can get desired product of aromatic amines. So next is nitration. Nitration of aniline. So direct nitration of aniline, we get ortho, para and meta product also. Because in that, when aniline is protonated in a strong acidic medium, it forms aniline ion, which is deactivating deactivating group, or means meta directing group. So what we can say? We can say direct nitration of aniline beside the ortho para product. Beside the ortho para product, a significant amount of meta is also formed. Means when nitration, direct nitration of aniline is being done, beside the ortho para product, we also get meta product. Because in the strong acidic medium, aniline is protonated and forms anilinium ion, which is meta directing group. Means if we say that in nitration, what we use? Concentrated H2SO4 and HNO3. So in a strong acidic medium, when it is being nitrated, beside ortho and para product, we get some significant amount of meta product also. Let us see what is that. Aniline plus concentrated HNO3 plus concentrated H2SO4, ortho, that is it is ortho, that is meta, and this one is para. So what is that? Ortho is 47%, para is 51%, and meta is 2%. So we can say that the nitration of aniline in a strong acidic medium, it gives meta product also, not only ortho and para, but meta product also. So if we want monosubstituted product, if we want para product, so what we have to do there? There we have to protect this one by acetylation. That by acetylation we can protect this group, and we will get the para product. Para product as a major product. So for para product, we have to protect this one by acetylation with acetic anhydride. Okay, and in that case we will get the product. Here like this, if we are protecting, if we want monosubstituted product, that will be para product. So we have to protect this one by the process of acetylation with acetic anhydride. So let us write what is that. Here, this is NH2, and we will protect this by acetic anhydride. Okay, and we will get the product like this. Here, NHCO CH3, and then nitration. So HNO3 and H2SO4 we will use, and we will get para product. What is that? Para product. So like this we will get. If we have product protected, then we will get para product, para nitro, like this compound we will get. Okay students, so this product will be obtained. And further, if we are hydrolyzing this, so means acidic or basic hydrolysis, we will get like this product, NH2 and NO2. So like this product, what we have seen here, if we want para product, we have to protect this group is H2 group because it is activating group. So we have to prevent this activation by the acetylation, and then we will get this product, and we get para product, para aniline. But if direct nitration we are doing, so in that case we will get ortho, meta and para product. But if we are protecting this group by the process of acetylation with acetic anhydride and followed by hydrolysis, we will get para product. Understand? So you should remember this for para product. For para product means for para nitro product, we have to protect this one by acetic anhydride by the process of acetylation. And for for the mixture of product, ortho, meta and para, direct nitration, when direct nitration of aniline takes place, it gives us ortho, meta and para aniline. And last is that sulfonation. Last is sulfonation. Okay, sulfonation. So aniline are heating with concentrated sulfuric acid. It forms sulfonic hydrogen sulfate. When sulfuric acid react with aniline, it forms anilinium hydrogen sulfate, which on heating at 553 to 453 to 473 Kelvin, it gives us sulfonic acid, and which one is also known as sulfonilic acid. So what we have seen here, when aniline react with concentrated H2SO4, it forms anilinium ion. This form NH3 plus, what is that? Let us see, anilinium hydrogen sulfate. It forms anilinium hydrogen sulfate, which on heating at 453 Kelvin to 473 Kelvin with concentrated H2SO4, it gives the product that is sulfonic acid. It gives the product as sulfonic acid. NH2 and sulfonic acid gives the product SO3H. Benzene sulfonic acid. This is the product. So what we have seen, when aniline is heated with concentrated H2SO4, it forms that anilinium hydrogen sulfate, which on heating with concentrated H2SO4 at 453 Kelvin to 473 Kelvin, we get benzene sulfonic acid, and this is also known as sulfonilic acid. And it shows resonance like this. So we can draw like this also. Okay, students, here we can show like this and like this product. Okay. What we have seen here, when aniline react with sulfuric acid, is formed anilinium hydrogen sulfate, which on heating with concentrated H2SO4, it forms aniline sulfonic acid, and which one also known as sulfonilic acid. Okay, and they both show the resonance. So in that, what is there in resonance? Like this resonance. So one most important topic, that is that aniline doesn't go Friedel-Crafts alkylation or acylation, because in that It forms salt with AlCl3, which is used as catalyst and that act as deactivating group.